Okay, welcome back. Now let's take our work we did yesterday and expand it a little bit, but really we want to focus on a practical application with the decay of a couple interesting particles. I found a good problem out there that I think is worth working. It gives us a chance to run through some questions of units and exercise the equations we developed and start getting us ready to really take off into more sophisticated relativistic mechanics. Okay, so let's begin. So let's look at the problem that I've selected for us. We are going to study the decay of the lambda baryon, the ground state lambda baryon, called the lambda neutral baryon. That zero up here is usually the sign of these subatomic particles. This I stands for the isospin. So down here you always get this IJP. So it's the isospin, the total spin, and the parity. So this is isospin of zero. The total spin of a half, so it's a 1/2 spin particle with a parity of plus. So this describes a little bit of information about the particle wave function. None of this matters to us. We are only treating these particles as things that go into reactions and come out of reactions. We're not concerned about the dynamic forces that work on them, where this stuff would matter quite a bit. But what we do care about is the mass of the particle, right? All of our equations seem to have mass. So this mass is the rest mass. They don't say that here, but of course, if you reach this point in particle physics, you should know that this is the rest mass. And the rest mass is 1,115.683 mega electron volts. Now, what they're not really saying here is what they really mean is, well, they mean mega electron volts. Energy is a unit of mass. So they're definitely implying here that they're measuring mass in units of energy, because the electron volt is a unit of energy. So immediately when you see that mass is being measured in units of energy, you know right away that they're working in a system of units where c, the speed of light, equals 1. And often what you'll see, and often in the particle data group stuff too, what you'll see is mass measured in MeV per c squared. They write it this way very often. And in fact, that's the way I'm a little surprised not to see it here. It's probably because, again, they know that you know it's MeV per c squared, where when c squared equals 1, it doesn't even matter. So I suppose the idea is they're asserting c squared equals 1, so they don't need to carry around this little c squared underneath that you often see in particle data group units. In fact, it's obviously a little simpler to understand when it's just MeV. But that's the mass, and we need that number. There's some other interesting facts here that are not relevant to us, but I'll check while we're at it. The idea is the mass of the lambda particle minus the mass of the anti-lambda. So the mass of the particle, the difference in the masses between the particle and the antiparticle as a fraction of the overall mass of the particle. It's given, that would be interesting, right? If this number here is not 0, that means the particle and the antiparticle have different masses. But you'll notice that the value is minus 0.1, but the confidence interval is 1.1, so it includes 0. So this difference may be 0. Likewise, the lifetime of the particle, the antiparticle, also includes it's an interval that includes 0. So that's kind of cool. The lifetime of the particle times the speed of light, 7.89 centimeters. I guess that's about as fast or as far as you can expect this particle to go. Although that's not exactly true because, of course, this is the proper time. I'm not sure how these particle physicists use this number, but it's the speed of light times the proper lifetime, meaning the lifetime of the particle in the rest frame of the particle. I guess if you Lorentz transform this to some frame where it's moving faster, you can get a different distance out of that. I'm not a particle physicist, like an experimental particle physicist, so I'm not sure how all these numbers would be used. The magnetic moment is another property of the particle. Again, it's not something we're going to worry about. The electric dipole moment of the particle, that's kind of interesting. If I recall right, those electric dipole moments should in general be 0 for particles like this. Especially for the leptons, it should be 0. I suppose for complex particles like the lambda, remember the lambda is an up-down strange quark configuration. So I suppose there's some possibility that these quarks can arrange themselves in a way where there's a little bit of asymmetry of charge and you would end up with an electric dipole moment. But regardless, the measurement is less than 1.5 times 10 to the minus 16 e centimeters. This is a unit of dipole moment, charge times distance. So hey, it could be less than that. It could still be 0, right? So interesting fact. Okay, but we care about the mass, right? So this is our takeaway, is the mass right here. Now we're also interested in studying a decay, so we'll pick one of these decay modes. And this group has all of these common lambda decay modes. And we're going to grab the first one here, the proton negative pion decay mode. It's 63% of the overall decays of this particle. The 63% of the overall decay width. This gamma here is the decay width. We won't go into this line shape of the particle visa, which would tell us something about its lifetime. But we do know that of all of these, the fraction of the decays, 63% of them are going to be into the proton and the negative pion, followed by 35%, which are going to be the neutron and the neutral pion. Notice these are charge conserving, right? The lambda has 0 charge. That's what this 0 is. This little 0 is neutral lambda. So when you see this, you have a positive charge on the proton, and this pion is negatively charged. Pions come in uncharged, negatively charged, and positively charged. So in this case, we're choosing it's still it's overall neutral, and here this is overall neutral. The neutron carries no charge, and the neutral pion carries no charge. But it seems that the decay mode favors this channel right here, this proton pion channel. Now we're not going to discuss why it favors that channel, because again, that has to do with the internal activities, the internal dynamics and theory of quantum field theory. We're not going to touch that. And then it also tells us the momentum, and that should be the final momentum of the particles. Now notice here, they do use momentum in MeV over c, right? So they're happy to report MeV over c, but for some reason they don't report MeV over c squared here. I'm not sure why, but regardless, that's just understand that. Well, we're going to go through let's go through the units right now. So that's all the information we're taking away from this, the most basic stuff. We're picking a decay mode, and we're looking at the mass of the lambda. Now we need to now know the mass of the proton and the mass of the negative pion. So I've dug that up separately, and so let's have a look at some of the unit questions. All right, so the mass of the lambda particle right here, it's 1,115.683 mega electron volts. So the mass is being measured in units of energy. When C is 1, of course, this little reference to C squared goes away, and we'll see how to use that as a reminder in a moment. But this is the mass as reported by the particle data group, mass in terms of energy in units where C equals 1. And the favorite unit of energy is the electron volt, which is the amount of energy electron accumulates when it is accelerated through 1 volt of potential difference. So what if we wanted to convert that to kilograms? You should all be able to do this, even though you won't need to very much. We're going to work exclusively in electron volts. But the first thing would be to take this and convert it to electron volts. So mega electron volts to electron volts is just a factor of 10 to the 6th power. And then that should, of course, give you this number right here. 100 and, well, I guess I'm missing a comma. Let's see, so that would be 1,115,683,000 electron volts, right? It's just a little more than 1 giga electron volt. And that's its mass in electron volts. That's after you convert to just raw electron volts, multiply by 1,000,000. Then there's the conversion factor of 1.6 times 10 to the 19 joules per electron volt. Joules is just this sort of familiar classical mechanic unit of energy. I don't know why you would ever use joules for this, but if you wanted to, you just have to dig up the conversion to your favorite unit of energy to the electron volt. And if you do that, you end up with 1.78509 times 10 to the minus 10 joules per c squared. And so with that, you now have the mass still in energy, but now the energy is joules. So it weighs 1.78509 times 10 to the minus 10 joules, right? And if now a joule is a kilogram meter squared per second squared. So if I divide by the speed of light, then I will end up with actual kilograms. So now I'm going to convert to a different unit of mass altogether. But to do that, I need to divide by whatever the relevant speed of light is. Well, the speed of light in the relevant units. So in this case, our speed of light, meters per second, because I'm dealing in just the units of the kilogram meter second. Here it is, 299,792,458 meters per second. And I've even calculated c squared here. And you do the division and you end up with 1.99063 times 10 to the minus 27 kilograms. So that's where this sort of c squared gets eliminated. If you finally do want to convert to a real mass unit, not an energy unit, then you remember, oh, I got to divide by c squared. And so I think you just track that c squared around to keep track of this fact. So that's the kind of units we're going to deal with. Or that's the nature of the MEV over c squared. But the point is, we're just going to work in the MEV units. That's totally legitimate mass. We set c equal to 1, and now everything's in MEV. So I looked up the mass of the proton. This is the best number for the mass of the proton, 938.27 MeV. And the mass of the negative pion is 139.570 MeV. Fun fact, the mass of the pion with a positive charge is the same, but there is a neutral pion, and that mass is 134.977 MeV per c squared. So the neutral pion actually has a little bit less mass, and these are all really interesting questions in quantum field theory about why that is. Of course, carrying around that charge has a lot to do with it, I'm sure, but because energy is associated with the field around the charge and all of these great, fascinating, wonderful things that happen in QED. I think that would be a QED question. But regardless, it could be a QCD question, right? A pion is a quark anti-quark pairing, so there is quantum chromodynamics in there involved as well. So clearly probably what's going on is the interaction between the quarks with the charged pions is enhanced with charge and is absent when everything's neutral, and because of that, there's a little bit less mass. Anyway, so we now know the masses of the three particles that we're dealing with. So let's go ahead and execute some of our calculations that we worked so hard to figure out last time. All right, so let's begin with our arrangement. We start in the center of mass frame with our neutral lambda particle. We know its mass here. I've also written down its lifetime. Since the lifetime was so available to us, I know we're not talking about the nature of the decay. I kept promising that, but I couldn't resist. The chance of it surviving with time as ticked off in the lab is e to the minus t over gamma tau, where tau is the actual lifetime of the particle. So in our case, the mean lifetime of this particle is 2.62 times 10 to the minus 10 seconds. After that, you got to multiply that by gamma, right? So some larger time than this, because the faster it goes, the longer it lives, right? Because its clock is what's ticking away before it dies, and its clock is multiplied by this gamma factor, which is going to be larger than 1 in the laboratory, because in the laboratory, of course, this lambda is moving along. So it's going to live in the laboratory longer than 2.62 times 10 to the minus 10 seconds, depending on what this gamma is. And this is the survival time, right? That means this is the probability that it will be still around after a certain amount of time, t. So that's kind of interesting. Anyway, we just pulled this right off the data sheet. So now we're going to do some basic calculations. And the first one is this: what is the magnitude of the momentum, the 3 momentum, of this pion and this proton after the reaction, right? What is the magnitude of this 3 momentum? And it is given by this expression, which we went out of our way to calculate. So now, for this mass, I need the mass of the lambda particle. And for mass 1 minus mass 2, since we're talking about the, it really doesn't matter, right? So it's symmetric because of the square. So here I'll put in the mass of the pion, and here will be the mass of the proton, and likewise the mass of the proton, mass of the pion, mass of the lambda. All you need are these masses, and that m out in front is the mass of the lambda. All you need are these masses, and you know the center of mass momentum of both particles. Because remember, in a decay like this, both particles have to leave with the same momentum for everything to be conserved, the same total momentum for everything to be conserved. So let's just do this calculation by inserting this number right in for m, and m. And we'll substitute the appropriate mass for the pion, 139.57 MeV, and for the proton, 938.2720813 MeV for the proton. Obviously, I'm going pretty long on significant figures here. The mass of the pion is not known nearly as well as the mass of the proton. That has a lot to do with the stability of the proton, for what it's worth. But that is an important point, is that there are some there's going to be a lot of rounding in the end. But I always like to throw in everything max that we know, and then in the end kind of figure out what the significant digits are. So if we plug these numbers in, what do I get? And after I plug in the numbers, I get this number, 100.58 MeV over c, not c squared, MeV per c for the momentum. Momentum is also measured in MeV in units when c equals 1. So now this is, remember, the momentum of each of these particles, the total momentum of each of these particles, because it has to be equal and opposite. And you may remember how we calculated that either last time or the time before. And but the good news is we can kind of check. Because if you remember when we looked at the decay mode, we saw this 101. And our number, 100.5 something, it rounds up to 101. And there's no decimal point here implying that I should be any more precise. So I'm going to declare victory, and we have calculated this value that's on the particle data group sheet. We calculated this number from first principles. That's kind of cool. That is kind of cool. Let's see. Okay, so what else can we calculate from this? Let's keep going. Well, something I'd like to know is the complete 4 vector, right? The 4 vector of this daughter particle, say the 4 vector of the pion. So I need the energy of the negative pion, and I need its momentum vector. Now, the momentum vector we kind of know, because it's going to be the momentum in the CMS frame sine theta, and the momentum in the CMS frame, the center of mass frame, cosine theta, and the y component will be 0. So I know that this will be the x component, this will be the z component, and the y component will be 0. But what about this e? Well, actually, I don't think we calculated the formula for e, so we need to do that very quickly. Calculating a formula for the time component of the 4 momentum of the daughter particles in the center mass frame is a lot easier than it was to calculate the momentum. There's a lot of algebra in that momentum. But let's remember the parent is just given by this 4 vector because we're in the center mass frame. So that means the frame of the parent. So the parent's moving, motionless. So its momentum components are 0, and its energy component is just its mass. So this E is actually going to be equal to m. The daughter particles, well, they have momentum and they have their energy. So we need to calculate this EA and EB. We've kind of already calculated, we have already calculated the momentum components. We just did that a split second ago. So let's see if we can calculate EA and EBs. So we're going to use conservation of 4 momentum. So I write the 4 momentum of the parent particle is equal to the sum of the 4 momentums of the daughter particle. That holds in relativistic mechanics. It does not necessarily hold every instant inside the decay process, right? There you now have all these Feynman diagrams and all of these off-shell calculations. But when we're looking at everything that happens before it goes in and after it's gone away and there's no interactions, this absolutely holds. So I'm going to rearrange this and solve it for PA, this 4 vector right here. PA is the parent 4 momentum minus the second daughter 4 momentum. And I'm doing that because what I'm going to do is square both sides and create the relativistic invariant of the first daughter particle and the relativistic invariant of the difference between the parent particle and the second daughter particle, right? That's this number here. This is the the difference in 2 4 momentums is a 4 momentum, and any 4 momentum squared is a relativistic invariant number. So and we treat it like a vector, right? So we got the relativistic invariant of the parent squared, the relativistic invariant of the daughter squared, and then we have this dot product between the two. And that's why this dot product is easy to evaluate as long as I did this step here, as long as I went from this to this, because of all of these zeros in the parent, it's very easy to calculate the parent dotted into this. It's only the first term that survives, right? E times EB. And that's exactly what we have here. So this gets replaced by 2 times the energy of the parent particle and the final energy of the second daughter particle. And of course, the energy of the parent particle is just m. So now I replace everything with their relativistic invariant notation. So PA squared, well, that's the rest mass squared of the first particle. This P, when it blows up, this P squared becomes a mass squared. This P sub B squared becomes the mass of the second daughter particle squared. And then 2EEB becomes 2m because E is the energy of the parent particle, which is just m, because we are in the center of, now we're taking advantage of the fact that we're in the center of mass frame where the 3 momentum is 0. The components of the spatial components of the 4 momentum are all 0, which means E is always going to equal to m. And so I can replace this E here with m, like this E here gets replaced with m. And then I can solve for the energy of the second daughter particle. And that solution is given right here. And of course, this is completely symmetric for the first daughter particle, which would be right here. So what is it? It's the mass of the parent plus the mass of the particle you're interested in finding the energy for, minus the mass of the other daughter particle. So this is very sensitive to what the decay channel is, because for lambda, this m will always be the same, but the decay channel can be very different each time. We've already seen how the decay channel can be any one of these decay modes. And, these do happen at some relative frequency, 63 and 35%, but here you've got, well, this is pretty small, actually. These other branching ratios are pretty tiny. And these are 3-particle decays, which we haven't studied yet. 3-particle decays open up a lot of possibilities for momentum. But the masses of these particles actually matter, right? And you can see they matter, right? Because of so the energy of the final products is really going to be very, very tightly related to the mass of the final products. The fact that this is a two-particle decay constrains things quite a bit. Okay, so let's calculate EA and EB. Okay, so I wrote down all the calculations here. So the fourth component, or the time component of the pion's 4 momentum, given by this calculation, and I run these numbers here. I put in the lambda mass, the pion, the negative pion mass, and the proton mass, and I get 172.035 MeV. Now notice that the pion mass is 139.57. So this time component, this total energy, is greater than the mass energy of the pion itself. So the difference between the two is going to be the kinetic energy of the particle. And that'll be true in any circumstance where these particles are not interacting with anything. There's no potentials around. That means they're completely free at the end and they're free in the beginning. So that's how we can get at, and we'll talk about the kinetic energy later, but right now you'll notice that it's bigger than the rest mass. With the time-like component of the proton's 4 momentum, or I run the same calculation. The only difference is the order that these two numbers are subtracted. It's a symmetrical equation in many ways, but the order does, the order matters. You can't just swap things around, and you end up with a whopping 943.648 MeV. And that also is a little bit bigger than the mass of the proton, but not much. The mass of the proton was 938.272, and this is 943. So there's only about 5 MeV of kinetic energy in the proton, but there is something like 32 MeV kinetic energy in the pion, which is kind of interesting. And again, since this is a decay to 2 particles, it's constrained. This was always the way it's going to happen. So we can double check this. Let's have an experiment. Well, let's test. This is now the 4 vector of the 4 momentum of a pion in the rest frame of the lambda when this angle, remember this angle that we had here? This angle here, theta, which is the angle off of the z-axis, if that angle is pi over 2, so all the momentum is in the x direction, which was this way. So if all the momentum is in this x direction and theta is pi over 2, then it's easy to construct the 4 momentum here. Otherwise, there'd be a sine theta, and then there'd be a component down here in the z direction with a cosine theta. But let's just get rid of that and just assume that we waited around until the decay was just right. And this now is the 4 momentum of the pion, and this is the 4 momentum of the proton. Now notice, actually, there should be a sign difference, right? There should be a sign difference. I think the way I have it set up is the proton is headed down, so there should be a negative sign in the in here for the proton. So they're not exactly the same in that second term, but the magnitudes are the same as we learned through the calculation. And now I've replaced the time-like component with the numbers I just calculated. So if I calculate the square magnitudes of these 2 4 vectors, I should get the invariant mass, meaning the rest mass of the particle. And sure enough, right, the rest mass of the pion, you do the calculation, it's 172.035 squared, and because of the Minkowski nature of 4 vectors, you subtract the square of the second component, and you end up with 139.57. Actually, you end up with 139.57 squared. The square root of it will be 139.57, which is exactly the mass of the pion. So that checks out. And likewise, it checks out also for the mass of the proton. There's really no reason why it wouldn't, right? I am reintroducing the MeV over c squared terminology. And so there is the answer. So we have now exercised this process of the formulas we created. We actually had to derive this formula here in this lesson quite quickly, but it's not a hard formula to see, not nearly as hard as the one that calculated this number here, right? This number here that came from It came from this formula right here. This formula was a bit of a bear to calculate. And we didn't really experiment with studying the angle and the center of mass in the lab frame yet. Okay, so that is it for today. We may do another example tomorrow. I think the next lesson, what we're going to do is we're going to actually go back a little bit, and we're going to study this relationship, P equals gamma mv. I've dug through some old books, and I found some fascinating material about the nature of the development of that expression and where it comes from, and I think it's definitely worth exploring. Okay, so I'll see you next time.